Hi, everybody. Today, what we're going to do is we're going to kind of piggyback off of our last lesson. So, we went through a slope introduction and we broke down the components of slope. And today, what we're going to do is we're going to kind of look at it now as about an application and a way that we can kind of tie together slope in some alternate forms. So, the first thing I want you to do is take a look at the problem on the screen. And what we should have then is the idea that point A exists on a graph, and we need to draw a line segment, AB, that has a slope of 1/2. So hopefully we're good, that coming through that last lesson, we're fine with the idea that slope is always equal to your rise over your run. And so when you've been told in that second sentence that the line segment AB has a slope of 1/2, we're actually being very descriptive. We're saying that we have a rise of 1 compared to a run of 2 throughout our graph. And so if the problem asks me to find possible coordinates of point B, what I'm going to do is I'm going to start at point A and move in the direction of the slope. And so if that slope says that I have a rise of 1 and a run of 2, then maybe I go up 1 unit and across 2 units. That would be me moving with a slope of 2. And that's going to cause me to finish at that location. That becomes one possible location for point B. And if I were to connect A and B using a line, I now created a very short line segment, but it has a slope of 1/2. So my possible location then for point B, if it's that blue point B, would now exist at the point 4, 4. I hope we can see, though, that there are many different answers to this problem. Actually, infinitely many. So what I'm going to do is I'm going to jump over to that second graph, and we're going to work our way through some alternate examples. The first assumption could have been that I didn't have to stop after moving according to that first slope. And so perhaps I said that I'm going to go up 1 and over 2, but maybe I did that same thing again, and I went up 1 and over 2. That could be the location of point B. And if I were to connect those with a line, then you notice that you create this green line segment with a slope of 1/2. Now, it doesn't quite look like a slope of 1/2 at the very beginning because my run was actually from 2 up to 6, so a run of 4 units. And my rise was actually 2. But we can hopefully see then that my slope is 2/4, which reduces to 1/2. So one possible way for us to go through and find more of my points, and you'll notice then that that creates infinitely many point B's. You could simply continue on moving as many times as you want, over 2, up 1, and creating as many other points on that line segment. The last thing I want to address is the other way, and it's not as common of a way, just as important of a way, though, to find another point B. That we get into this habit of always taking the sign of our slope, and we notice that our slope is positive, so it rises to the right. However, my slope is also a fraction. It's a comparison. It's a ratio. And so if I chose to move left 2, then that would be a run of -2. That for me to have a slope of 1/2, I would then have to move down 1. And we just get a little confirmation that -1 divided by -2, a negative divided by a negative, is also a positive. And so maybe we backtracked and came up with that as our location of B. So we have many different answers for what B could be. Alternate examples on that second graph could have been that I went over 4 and up 2. Or maybe I went backwards 2, and I went down 1. Many different ways, infinitely many ways. So what I want you to do is just take a look at question 6, and I want you to give it a shot. So pause the video, and we'll come back and we'll see if we match up. Okay, we're back. The only reason we threw problem 6 at you is because oftentimes you may struggle a little bit more when you see your slope being a whole number or an integer as opposed to a fraction. Just keep in mind that when you have a slope that's equal to an integer, you can always go back and think of it as a fraction. And so when we see that integer, we need to know that we have a rise of -4 for every run of 1. And so very quickly then on my graph, maybe I went over 1 and now down 1, 2, 3, 4, and came to a finishing point on B. Or perhaps I went backwards 1 and therefore up 1, 2, 3, and 4. Perhaps that's my finishing position for B. So, 2 possible examples you could have come up with. The first one, if you thought in terms of those directions, maybe we came up with that location. Or on that second graph, if we backtracked a little bit, perhaps we got to that location. Okay, now I want you to take a look at problem 7. I want you to notice that problem 7 is just like problem 5 and 6, except we've taken away the picture. Sometimes without providing you a graph, you think that you're supposed to do this using an algebraic means, and I want to go through with you guys 2 different ways to be able to work your way through it. The first thing I would always recommend is if you like using a picture, then feel free to put down a quick sketch. So maybe I put down a quick X and Y axis. And so I start to think then about the location of where C would be. Well, if I'm at the coordinates of 4, 7, then I have to go to the right 4, so right a bit, and up a little bit more. Perhaps that's my location for 4, 7. So if I just clean that up a little bit with my axes, then you can think of point C being in this location. I need to label the coordinates of point C because I don't have a grid to be able to read the coordinates. Well, now what that says is my line segment has to move according to a slope of -5/3. And so I have 2 options. I can think of that slope as having a rise that's negative and a run that's positive, or I could think of it having a rise that's positive and a run that's negative. Either of those fractions equals -5/3. Just make sure that we don't apply the negative to both the rise and the run, because we know a negative divided by a negative equals a positive, and therefore we would have an incorrect slope. So to go through and use a picture to go and solve that problem, then maybe what I do is I think of my first option. That I'm thinking, okay, I'm going to go through and move down 5 units and to the right 3. That's going to arrive at a certain point D, and I could find those coordinates by going down 5 from 7, so I have a y value of 2, and to the right 3 of 4, and therefore 7. The alternate solution to that would have been backtrack. So perhaps instead I thought of a run of 3 backwards, so negative, and therefore up 5. That might have finished at this location of point D to go back 3 on my X and to go up 5 on my Y. either of those values for D, coordinates for D would be good. We know from the previous problem you could have continued on, but those would have been the two solutions, or two of the most common solutions we would expect. Lastly, I just want to be very careful if we thought of this algebraically. If you have point C, which is at 4, 7, and we're moving according to a slope of negative 5/3, we just need to remember that my slope is my rise over my run. And my rise always makes reference to my my y values, and my run always makes reference to my x values. Rise being vertical, vertical or y's, run being x's, x's are horizontal. And so if I wanted to calculate that, I could very quickly say, if I was going option A, then what I need to do is I need to move 3 to the right of my x value, and I need to move 5 down from my y value. And so we come as the location of D at 7, 2. Or perhaps we take a look at option B. If I started at 4, 7, then what I need to do is I need to take away 3 from my x value, and I need to add 5 to my y value. And so maybe our location is at 1, 12. I definitely think the picture is going to help you guys to be able to argue your way through. Two options, though. Okay, now I want you to take a look at problem 8. 8 is an application question of us talking about a slope. And this is a pretty basic application question for us. The biggest part is the problem asked us to calculate the rise when making reference to slope. And so therefore, if I recall that slope is rise over run, then I can take the information in the problem and I can sub it into that relationship. I've been told that there is a slope of 2/5. I've been told that it happens over a distance of 45 meters, which means my run is 45. So, therefore, I need to find the rise. Maybe I just plug in a variable like x. If you don't like that, then feel free to keep the word in that relationship. You are solving for rise. So, two different ways to go through to solve for your rise. The first way can be proportions. That what would you do to 5 to turn it into 45? You would multiply that by 9, and therefore you would have to do the same thing to 2 to keep those equations equal, and therefore your rise is going to equal 18 with our units. Or, given 2/5 equals rise over 45, you may view to solve that like an equation, which means to get rid of a divide by 45, you need to multiply by 45. That line you're probably not showing because you'll calculate 2 times 45. And now we make our division, and so we come up with our rise being 18, and put in your units. So, hopefully just a couple of applications of slope. Now what we're going to do is we're going to kind of change gears a little bit. I want you to take a look at the top of this page because there's an important relationship that we're going to talk about if we're given a series of coordinates within a relationship. And what we need to examine is something called finite differences. And so, here's an example where we're talking about Lucia's plant height measured at a number of days after she planted it. So, when we take a look at that table, you now have information that 4 days after planting, the plant has a height of 8. Then 7 days after planting, it has a height of 10, and so on and so on. If we wanted to look at that and ask ourselves, is the growth of that plant Is the slope linear? Then we have another way to examine it without producing the picture. So for a lot of us to be able to try that, we would want to graph that relation. We need a faster way. And so what we're going to do is we're going to examine something called finite differences. What finite differences is a means for us to calculate slope within a table. So the first thing we're going to do is we're going to examine how we move from one point to another point. How we move from one point to another point. And we're going to examine then the moves from the point 4,8 to the point 710. Now, we don't need to write out that red at all. But really what we're going to look at then is the movement within those points within the table. So, what do I do to go from 4 to 7? Well, how many days have passed? And for us to calculate that, what we actually do is we go backwards with our arrows. So, rather than moving from 4 to 7 in calculation, we say, what did we do to 4 to get to 7? We actually added 3. And over the course of those 3 days, what happened to the height? Well, it would be an increase of 2 centimeters. So we just did a quick calculation of 7 minus 4 and 10 minus 8. Really what we just did within that setting is we just calculated the slope of moving to those 2 points. Notice that on a quick sketch, if I was to put a point at 4,8 and then another point at 7,10, really what we did was we examined that we went to the right 3 and we went up 2. Perhaps you can see the slope within our finite differences. My slope is up 2 over 3. So all that stuff that we just sketched off over on the right, we're going to get rid of that because we can examine that slope then to determine, does this table represent a linear relation? So my next movement would be from this point to this point. So we noticed that we went over 3 units and we went up 2 again. Now we examine our movement to the next points. You went over 3 and we went up 2. And what we just found then was throughout that equation, that table, we have a rise of 2 and a run of 3. And since my slopes were always equal, therefore, that table represents a linear relationship. That is us using finite differences to determine whether something's linear or nonlinear. I'm going to throw one more problem at you so we can see how this really comes into play as we start to compare them. Lastly, on the screen, what you're going to see are 3 tables. We have variables of n and variables of p. My n is going to represent a number, and my p is going to represent a number. My n will be my input, and my p will be my output. So within every table, then, I have the means to use finite differences to determine which one of these tables represents a non-linear relation. So let's look at table A. For me to examine that, I'm going to calculate finite differences, which means I'm going to determine my slope. For me to go from 1 to 2 means I went up 1. Well, I notice that in my n column, I'm always going up 1. I am moving for consecutive values of n. Now I look at my y column and I notice that I went down 3 and down 3 and down 3. And so if I notice within my finite differences, everywhere where I moved from one point to the next point, that point to the next point, and so on, I was always moving according to a slope of -3/1. And since it was the same all the time, I know that that means it's a line. If I was to jump into B, B's table looks a little uglier because we have some decimal coordinates. But I'd like you to go ahead and determine your finite differences on B. So pause the video now and give it a shot. Okay, we should be back, and you'll notice that as you move from your point N to N, we went up 5, and up 5, and up 5. You'll notice that between P values, we then went up 0.75, up 0.75, and up 0.75. I'm going to be honest with you. I don't even need to calculate slope in this instance because I notice on every single one of these movements, my slope would be the same. And therefore, without even calculating what 0.75/5 was, I can then say, yes, it is a line. Now, for us who really wanted to make sure we calculated, well, 0.75 is really 3/4. There's my rise. My run is 5. And so if we reduce that, maybe we got through to an actual slope of 3/20. Okay, let's take a look at our last table. In C, I want everybody to pause it, give it a shot. We'll see what we come back with. Okay, we're back. And so, as we worked our way through, we would have noticed that we went up 3 units, and up 3 units, and up 3 units. And so it's starting to look that this is going to be a line again. But then we notice that in my p-values, I would have went down 9, then down 7, and then down 5. And so if I just went through and did a couple quick slope calculations, then my slope between my first 2 points is going to be -9/3, which is -3. However, if I then went through and calculated my slope in each case, my slope between my second and third point would have said that I went down 7 over a run of 3, and these two slopes are not equal. That would be enough for me to say, therefore, that is non-linear. Now, you may have gone through and completed that table. Maybe you were calculating a third slope, and you got down to this. But that was not needed whatsoever, because as soon as I find that my slopes are not consistent everywhere, then that graph is nonlinear. So, hopefully that helps you out with a little bit of an extension on how we can use slope. And then also the way that we can determine slope using something called finite differences. So now, time to get a little bit of practice, jump into the work on your weekly schedule, and hopefully everything goes well. Good luck.